Hello and welcome back. I hope you're doing well. Happy New Year's. Um, I don't know if you can hear it in my voice, but I'm a little bit congested. I think I'm in the process of getting sick at the moment, unfortunately. Um, I think I was infected over Christmas, and yeah, I've been feeling off since yesterday, and today my throat hurts and my nose is stuffy or runny, and so we've been struggling a little bit, but barring that, everything's good, and yeah, so I apologize if it's a little bit muffly. Hopefully, you see that the audio quality improved slightly. I tried to experiment around with the audio a little bit. Um, so yeah, so hopefully it's a bit clearer, a bit cleaner. Yeah, and I'll keep trying to improve little by little. I wanted to pick up though where we left off last time and talk about one aspect of the problem that we didn't really discuss last time. So briefly to summarize from last time, we talked about timelines, and we kind of broke down what the phases are between now and doom. um, and we broke them down into essentially three distinct stages. So there's the pre-crisis stage, which is the stage we're in right now, where models are not really capable enough, that their misaligned behavior causes like serious crises. At some point, that will no longer be true, and then we'll enter the crisis stage, and we'll get our warning signs. At first, there will be smaller in scale, and then larger and more intimidating and intense and dangerous. And then at some point, we'll reach a point. This is the point of no return, where now the models are capable enough that if they are misaligned, then there's really nothing that we can do about it. It's too late to act. And so I kind of discussed a little bit how long I think the different periods would be, and I made some arguments based on trends that groups like Metr have identified about how quickly model capability is improving, to give like a rough estimate of how long different periods are likely to last. And I noted last time that probably this crisis phase, if you're assuming that model capabilities are doubling every 7 months, and that pretty much within 2 orders of magnitude, if you increase model capabilities by 1 to 2 orders of magnitude, that you could go from noticeable risk to existential risk, then then the calculation is that this crisis phase would last somewhere between 2 and 4 years. And really, in a way, this crisis phase is the critical phase. It's the crucial time period. In the pre-crisis phase, you're like preparing, you're getting the message out there, letting everyone know, putting your prediction as to what is happening in the public consciousness. And then in the crisis phase, that's when there are issues and people begin to pay attention. And that's when you have to act. So if this is the critical time period, if this is the critical period in this narrative, in the story, then it's important to get an idea about how long this period is. If it's short, then then the timeline that we're looking at is inherently a lot more dangerous, because that window for acting can be very narrow. If the window is 1 day, then we're screwed. Then it's over. Or if we don't get any warning signs, if we cross over into existential risk territory immediately, then that's a very difficult situation for us to be in. Because it's hard to get people to really pay attention en masse and act in a coordinated way without some galvanizing event. So that's a very difficult. This question is really a critical question. How long is this time period? And I talked in the last video about one scenario that you can get almost no crisis period. And that's the situation where these companies are building massive data centers, they're scaling the current architecture. Some academic group discovers a new architecture that's better at scaling, that's performing better at smaller scales. And all the companies jump on this new architecture and begin training with it on their massive data centers. And then we could see a discrete jump in model capabilities. And so that could leave us with effectively no time to react. And today I wanted to talk about another way that you could shorten, another plausible situation that would shorten that time period for for this crisis phase. And this is the threat of recursive self-improvement, of models that when they reach roughly human level capabilities, especially at building new models, at AI engineering, that they can drive their own development and accelerate the trends that are outlined by organizations like Metr. So it's effectively, the idea is that if you reach a certain level of capabilities, you reach some threshold at which the models can very significantly, can even drive AI development. And at that point, you're no longer hindered by a lot of the things that are contributing to that 7-month doubling period. You are taking a lot of those restrictions away, and it makes sense that you can have a very rapid takeoff in capabilities from that point forward. So the doubling rate might go from 7 months to like a few hours. And so now this is an interesting situation to look into and to think about. And I think in theory, absolutely. Like, if you're saying that these models are generally capable and they're specifically capable at solving difficult technical problems, which is like essentially where they're excelling, well, building better models is a technical problem. And so it's I feel like very straightforward to extrapolate out that yes, that would happen. Models would become way better at building new architectures that are more efficient, at a lot of clever techniques, at maybe improving training or efficiency, maybe a better training algorithm altogether. So I don't think that humanity stumbled upon the optimal training strategy, the optimal architecture yet. And we actually know that that's the case because we have an existence proof with the human brain. The human brain is trained with a lot less data, right? And yet with less data, with less compute, with less electricity, we are able to outperform models in a lot of domains that require, thinking and deep reasoning and insight. So I think that it's very likely that there is an architecture out there, that there is a training algorithm out there that would 100x, 1000x, 1,000,000x model capabilities. So if you have models that are as good at solving these kind of technical problems as humans, they can contribute to that. And models can run in parallel. They can run 24/7. They can run superhuman speeds. So you can already see that you can very easily slip into a world where models are essentially producing their successors very quickly, and so you get a runaway effect, a positive feedback loop. Models become more capable. They can have new insights, and creating more capable models, allowing them to improve on themselves even faster, and so forth and so on. So that's the problem. It's a very serious problem. Now, the one thing though that I did want to point out, and I'll be interested to see what everyone else thinks, is how models are currently trained and how they behave in deployment is actually not conducive to this runaway effect. It's actually kind of like in our favor a little bit, because of two things. First of all, a full training cycle for models takes a long time. Like, I have to go back and check the exact numbers, but I think for the frontier models, they run them, the training, pre-training on those models, they run them for like months, like 3 months, I think, or 6 months, something like that. I think it's 6 months. So that's a long period of time. And then once models are actually trained, then they're deployed with their fixed weights, and those weights, as far as I know, are not changing. Now you do have things that are changing, like like from conversation to conversation. You have the context is changing, the input that you're feeding into the model. But the base model itself, the weights of the model itself are not changing, or there might be some like post-deployment fine-tuning that I'm actually certain that the companies are doing some post-deployment fine-tuning on the models. But even then, you're changing the weights just a little bit. You don't yet have a situation where models are continually adjusting their inner weights, much less adjusting their architecture. So in a way, that's to our favor, because if you have a model and it's very good and it comes up with a new architecture, or a new training paradigm, training algorithm that would outperform what it's doing now, then it wouldn't just be able to implement that immediately. It would be that would be the material that is used to train its successor, which is a process that will require a lot of compute and a lot of time as of now. So I do think that with the current architecture, especially if you're considering, and yes, you can say that, but models, if they're very capable, they can be very sneaky. They can perhaps do something tricky where we're not aware that they are changing themselves or that they are training their successors. So they can kind of do it in secret. And I think that is possible, but you have to think that initially, when we enter into this crisis phase, that initial period, models are still not going to be that capable yet. They're going to make still like some pretty basic silly mistakes at the beginning. I think the first warning signs will come a lot sooner than that level of deceptive ability. So as it stands now, I don't think that models will be able to just run away, take off like self-improvement, unless they are allowed to do this unless there is a platform built for this, which a lot of companies are saying explicitly that their goals is to produce an AI engineer, like a self-improving model. This is the goal that they put for themselves. And of course, that is an extremely dangerous thing. As also are schemes that try to improve model capabilities by having the weights, like having continual learning, having the weights of the model itself change as the model acts in the world, as it's inferenced. So that would also be dangerous, because models can then, if their weights are changing, if their weights are static, then it's easy to always check that nothing too crazy is happening. You can go back and validate that the weights are, in fact, have remained the same, that nothing sneaky is happening where the model's trying to adjust itself in some way. But if you take that away, if you allow updates within the weights post-deployment, then that increases the risk that models will be able to actually self-improve significantly and rapidly. So the way to think about it is, models, if they are capable, will be able to improve. They can build scaffolding for themselves, for example. That doesn't require changing their own weights. They can build superior scaffolding for themselves, and this has actually already been done, where a model produces scaffolding for itself that increases its own performance. So that's definitely possible. And the context, so a model can play with what information it feeds to itself for its context, how it uses the tools at its disposal, which is part of scaffolding. So all of that is within the model's control. So you would actually I could very well see that as models begin to improve capabilities, that you would see this effect where post-deployment, they get a little bit smarter. They get a little bit more capable. And it's because the model is kind of able to, if it's allowed to, like in an agentic context or something, is able to improve its own scaffolding, improve the information that it's using as context for different tasks, depending on how much latitude of action you give it. You can get that improvement. If you allow the weights to change, then that amount of improvement that you'd expect to see, that might grow very substantially. So that's something that we should be very careful with, because that's the dangerous situation where you can have a model that post-deployment is rapidly improving. Now, what a model like that might be able to do, though, is it might give us a better training algorithm, for example. But it would ultimately be, if you actually try to use that better training example to run a better model, assuming that it still requires massive compute and stuff, then it would be something that probably it would be hard to carry out in secret. It would be something that would take a long time, and that might be that would take a long time and a lot of data centers, and it would be hard to hide. But then again, if you come up with a training algorithm that requires 1,000,000 times less compute, then yeah, a model would be able to train its successor in secret. So that's another problem. But hopefully, in those early days when you get the first warning shots, we won't yet be at that level We won't be at the level where a model can come up with an architecture or training algorithm that's a million times better and then run it somehow in secret, though that can't be ruled out. So I hope, yeah, I hope that is useful or helpful. I think this is a very interesting area to consider because, like, fundamentally, people who bring up this point are correct. When as models improve, they will be able to improve themselves. And I could very easily see that this would break the trends that we're seeing right now in terms of how quickly models are improving. But yeah, but I am still doubtful that would happen towards the beginning of this crisis phase. And given currently how models are actually trained and the architecture that's used for these models, I think that it wouldn't be as straightforward to get like this runaway self-improvement effect unless someone is actively gunning for that, which, to my astonishment, some people are. So, yeah, that's pretty much it. That's all I wanted to say. So, thank you very much for listening, and I hope you have a very, very good 2026. And yeah, I'll talk to you guys in the new year. Thank you.